Welcome everyone. Today's webinar, like all webinars, is being recorded and will be available for on-demand viewing through geodynamics.org. During the webinar, please use the chat window to type in your questions or communicate with others. If you have a question during a Q&A session that you would like to ask via microphone, please use the raise the hand icon before turning on your microphone. Today, we are very fortunate to have Dr. Rene Gassmoeller of the Computational Infrastructure for Geodynamics at UC Davis. Dr. Gassmoeller's research primarily focuses on using computational fluid dynamics to understand convective processes in the Earth's interior. Rene is also one of the maintainers of the CIG mantle convection code aspect and has taken a leading role in both developing numerous key features and managing the incorporation of new features by members of the community. In addition to his work with Aspect, Rene has also worked on broader challenges related to scientific computing and software as part of the Better Scientific Software Fellowship Program. Today, Rene will be discussing this fellowship, which focuses on discovering and addressing social challenges during the evolution of scientific software projects. And with that, Rene, the screen is all yours. Thank you.
Thank you. Since you made me a co-host of this meeting, could you see if you see my Zoom controls on your screen, or am I just sharing my slides?
I believe now you are just sharing your slides.
Okay, that's perfect.
I think that's true.
Thank you. Okay, welcome everyone. Thanks for joining for today's webinar and giving me the chance to present these results or to start a discussion about better scientific software communities. As John said, I want to talk about social challenges in the evolution of scientific software projects. And this webinar will mainly consist of two parts. The first part will be about the question, why should we talk about software communities? What is the purpose behind it? And why is it important? And the second part will be about what do existing software communities do? What makes them successful, or what contributes to that success? So first I want to give a bit of background about myself and my viewpoint on these questions. As John already said, I'm one of the maintainer of Aspect, a computational fluid dynamic solver for computational geodynamics, and the types of models that this software computes is something like this. For example, the interaction between a rising mantle plume and a mid-ocean ridge and the generation of new oceanic crust. So I'm a computational geodynamicist by background, and I started off as one of the users of Aspect, as a scientist who wanted to use the software. And then I started to contribute features to that software and later became one of the maintainers of Aspect today. Over that time, the project grew from about 4 users in the beginning to now over 60 people who have actually contributed code to the software, and probably several hundred who have used it in some form. I'm now working at the Computational Infrastructure for Geodynamics, and as part of that work, I have interacted with a larger number of scientific software projects, both within CIG and outside of CIG. And as John said, in 2019, I was awarded the Better Scientific Software Fellowship of the Department of Energy's Exascale Computing Project to investigate these communities of these software projects. So why is talking about the communities important? Over the past 10 or 20 years, we have developed a large set of tools around the development of successful scientific software projects. We have tools for version control, like Git or Subversion. We have tools for code review and collaboration, like GitHub, GitLab, Bitbucket. We have lots of tools for setting up test suites for these software projects, for these softwares that we use. We can make the software portable. We can include documentation in the source code and generate automatic online documentation from it. We are making progress in the reproducibility of scientific software, in particular using containers. And we are working on increasing the scalability of software and measuring this scalability. But not only do we have these tools, we also have the best practices around these tools. we know how to use them, and we have guidance for how to use them and to implement these best practices. For example, there is a large collection of blog posts on the Better Scientific Software webpage. There is a webinar series by the IDEAS project that is purely dedicated to high-performance computing best practices. On the basic level, there are the software carpentry lessons, and CIG maintains its own list of best practices for how to set up and use these tools for scientific software. And there have been publications and books about the topic. So in a sense, we could argue that we learned all of the lessons that we need to know. We know how to build successful scientific software. So what can possibly go wrong if we just follow all of these lessons? But as we learned within CIG over the years, a lot of things can go wrong, even if all of these best practices are followed. Because a project is more than just the source code and the data that belongs to it. It is the community that works around this software data. And these communities are very diverse and often unpredictable. You don't know who will join your project and what purpose for what use they have for this software. So maintainers must continually reevaluate who joins the project and adjust the policies and the software architecture to meet those needs. There was also a recent Better Scientific Software blog post about this topic by Wolfgang Bangert, who's on this webinar, about how the personality of the leader reflects what the community thinks about the software or what kind of community is formed. So before I go deeper into the ideas about the best practices for communities, I want to make a quick break and talk about the words that I will use during this talk. When I talk about a user, then we usually mean a person who uses the software, who applies the software. A developer or a contributor would be a person who changes the software. And a developer can be a user as well, but they don't have to be. A maintainer is someone that not only changes parts of the software, they are often also developers, but they also take some sort of responsibility for the project as a whole. So they care for the software as a project. And finally, the community of a software project is actually everyone involved. That means the maintainers, the developers, the users, but potentially also PIs, or people who provide funding for the project, or people who provide outreach for the project. So it's actually a bigger category than only the three previous categories. Separate from all of that is the software itself, which means the source code, the tests, the documentation, which kind of all belong to the category of software. And finally, if you think about a software project, then the important idea here is that the software project consists of both. It consists of the software and of the people around it, the community. Since these are concepts that will come up a lot in the rest of the talk, I would like to make a quick break here and ask if there are any questions so far, either in the chat or unmute your mic. Okay. If there are no questions, then let's go on. So what will go wrong? When I started at CIG, I tried to come up with a short list of things that could go wrong or that have gone wrong in projects that I have seen. And they generally fall into three different categories. The first one would be interactions between the community and the software, trade-offs between competing goals within the software project, or leadership and governance problems. In terms of the interactions between the community and the software, a very important role is played by the architecture of the software that is used. An architecture that is useful can support the growth of the community. It can easily adapt to new problems, or is very well suited to the type of problem that the software is applied to. But architecture that is either very complicated or very brittle can hinder this growth. So the architecture of the software already determines whether growth is possible with that software. Secondly, the mood in the community, the feeling in the community influences the size and the quality of the core architecture. The more the people feel it is useful or welcome to contribute to the core architecture, the more this core architecture is actually improved and worked upon. But this work on the architecture and also the work that tries to grow the community is, although it's necessary, it's often not acknowledged, at least in scientific terms, in terms of scientific credit. So that is one of the other problems that can appear in this category. Then there are trade-offs between competing goals in the software. So for example, a certain change can be good for one user or one group of users, but bad for others. The typical trade-off is the one between performance and flexibility. These problems can usually be resolved using modern software development strategies. For example, encapsulation, polymorphism, templates, all kinds of things that make the software more flexible for different purposes without costing too much performance. But the community needs to align these goals, for example, at developer meetings. If people are not aware that this conflict exists, then they cannot resolve it. And that's equally true for the maintainers of the software project. Because as the project grows, maintainers might not be aware of what users actually want to do with their software. And so they don't know about the problems and therefore also can't fix them. And finally, there are leadership and governance problems. And some of those are related to the growth of the project. Typically, a small project requires a different organizational structure than a bigger project. And as the project usually wants to have some horizontal growth, meaning more users, you also need more people who take up responsibility for the project to keep up with the maintenance burden and to keep up with the community work that is necessary. So if this horizontal growth is not accompanied by vertical growth and user engagement, that can lead to the case where maintainers just say, this is too much work, I don't want to do this anymore. As the community grows, of course, it's also harder to communicate the design decisions of the basic architecture to all of the users and to explain why the software does certain things the way it does. And this also grows harder the bigger the software project becomes. Finally, for larger communities, or also for smaller communities, the new users need to feel welcome in the community. Otherwise, they will probably go looking for some alternative to that software. And finally, in all communities, there can be conflicts between members, either because of features or because of personalities or because of policies in the project. And these conflicts need to be managed in some form and cannot be ignored. So all of these challenges are somehow related to the community, either because of the interaction between the community and the software, or the interaction of the community with other parts of the community. So this led to the question, why is community management not in the list of best practices that I showed you earlier? Why is it not one of the common things that scientific software projects should do to follow best practices, to be a recognized successful software project? And this is all the more surprising because for general open source software projects, this is actually widely recognized. There are websites like opensource.guide, which was initiated by GitHub. There are full books about producing open source software and all kinds of community work around open source software. And there are many blogs of open source maintainers who discuss the question of how to effectively manage software communities. For scientific software, this question is not as much discussed. And in my opinion, there are three main reasons for that. The first reason is that we often argue or have in our mind the thought that whatever software is best in technical terms is the one that will be used. And therefore, community doesn't play a role. The second question or problem that arises is that we are still having problems of proper attribution towards the authors of software, at least in the scientific world, so that there is still the impression that many codes are hero codes. They are developed by one person or by one institute. And this person or this institute gets the full credit for the software because it circumvents the whole problem of who should get recognition for a software. And finally, most scientists didn't become scientists to become community managers of a software project. It's something that we are not trained to do and something that we probably didn't think about when we started being scientists. So we don't have the training and we are not aware of the fact that we might need to do this. But why is it important? So in a very simplified summary, we could say that the size of the software community limits the impact of a software project. The larger the number of users of a software project, the higher the probability that one of them will make an impact with that software. Of course, that's very simplified, but in a way, the distribution of a software controls how important that software is. And the size of the community is, of course, bounded. It will depend on the application of the software. If you have a very specific target area for a software, you cannot expect everyone on the planet to use it. But it also depends on how easy it is to use the software. It also depends on how much support exists for using that software. And it depends on how welcome people feel in the community around that software. So these are points that could be improved. On the other hand, creating such a large community obviously creates work. If you have more users, that means you get more questions. You get more requests for new features. People will find more bugs, which is of course good, but creates more work. And you will have more conflicts within those people. So in summary, efficiently managing a community improves the impact of the software and saves time compared to having that community without an efficient community management. And from all of these thoughts, I kind of constructed this idea of my BSSW fellowship project, which I called BSSC, Better Scientific Software Communities. And the idea behind it was to go out and look at successful scientific software projects today, see what they do, how do they manage their communities, try to collect that knowledge and distribute it as guides or as articles or as presentations like this one, in order to prepare new maintainers of new software projects, but also to start a discussion and a community of practice between people who already maintain software projects. Maybe even thinking about these questions already improves the state of our community management. And if you take one thing away from this talk or this webinar, then it should probably be that a software project consists of the collection of source code and the community that surrounds it. And that we should probably think about how we manage this community around it. And with that, I would go to the second part of the webinar, which will be a tour through all of the guides that are currently under construction about these topics. But before we go there, I wanted to give another chance for questions. I don't see the chat, so if there are any questions in chat, somebody would need to notify me.
I do not see any questions in the chat, Rene.
Okay, thank you. So one of the first challenges of a new maintainer would be to start a new project. It's not something that every one of us will come into regularly because it's not a situation that appears always. Many people just join existing projects. But it's nevertheless helpful to think about the steps one could take to plan ahead for how to create a community around a new project. And in essence, this could be summarized by 4 steps. The first one would be to define what your software is about, which essentially means defining a mission and maybe a vision for the project. To give you an example, Aspect's mission at the moment is to provide the geosciences with a well-documented and extensible code base for their research needs. That can probably be made a bit more specific than we have it at the moment, but it still has important concepts in there. Like, we want the code to be well documented, we want the code to be extensible, and we want to make it in a way that it's applicable to research needs. It's not a teaching code primarily. Then the next step would be to think about who is the audience of this code, and who would be most likely to use this code, and who would you like to advertise it to? For example, is it more for application scientists? Is it more for people who work on the methods? Which subdisciplines might be most interested in this project, and which career stage would be most interested in this project? And with this knowledge, you can go out and try to find capable and committed early users. And the important part about this is that most of the people that will join your project early will become the most important people later in your project, because they know as much or nearly as much about the project as you do. For example, all but one of Aspect's current principal developers were at our first user meeting in 2014. So there is a history there. Although you might lose some people because they move on to different projects, whoever will start to use your software will likely stick around and take up important roles in the project later on. And of course, finally, you have to work with them. And the important part here is that you have to work with them because it will create success stories for your software that you can use to advertise further to new people. So in this early stage, you work as much for the success of your first users as for your own software and for your own applications. The second topic deals with spreading the idea of a community software among scientists. And this can be difficult in different communities. We know that open software is important in many ways. For example, they tend to have less bugs. They tend to create more participation for users who wouldn't have connections to that kind of software otherwise, who cannot get a closed code. They tend to generate more citations, and increasingly funding agencies require open source software as a research product. And there's a great ideas webinar about this. I will provide a link to all of the ideas webinars at the end of this webinar about the concepts behind software licensing and which requirements exist. Nevertheless, there are common objections against making science software widely available and spreading all of the ideas and techniques behind them. One is intellectual property, which essentially means I spent so much work on this, I shouldn't be forced to just distribute it to other people. Another one is scientific reputation. The common argument is people who use my software and don't know it well enough and misapply it will create bad results that will then make my science look bad. The third one is scientific productivity, which essentially says, I have to spend a lot of time to make my software usable for other people. Why should I spend that time? And there are a few other objections, and they are listed, for example, in the Ideas Webinar 21, Software Sustainability. But most of these arguments are made without having a lot of experience of actually managing a scientific software project or a open community scientific software project. There are ways around these problems, and there are arguments that can be made against them. One easy to demonstrate argument is to have a modular software architecture, which allows withholding parts of the algorithm for a certain time, and then an easy merge later on at the same time when the publication is submitted or at the same time when the publication is accepted. A modular architecture, we will come back to this, also has some other very important benefits, like allowing multiple versions of the same algorithm or of different algorithms in the software. And finally, one important point here is to find the right pressure points to convince people. One point is to address their fears. As I said, there are arguments against most of these common fears from spreading open source software, but still it needs some courage to make this step. And there will be setbacks and there will be discussions about how to work around problems. So it's important to not only say that we are convinced there are multiple benefits to sharing the software, it's also important to be persistent and to accept that it takes some time. Another common challenge in the evolution of community software is to balance the work on the structure, which is important to improve the community, and the science outcomes of the software. So the architecture is critical to develop a good software, but developing that architecture takes a lot of time. At the same time, the community of software often expects growth. It expects new features, or it expects improvements. And all of these competing goals tempt maintainer to fudge things, to just hack something together that works, which usually will be more costly in the long run. This is summarized in this XKCD cartoon about how to write good code, which essentially says you have the choice between making things right or making them fast, but in neither case, you will arrive at good code. But there are strategies around this problem. For example, oftentimes it's possible to combine work on the structure with a certain scientific application. And I will come back to an example later. It is possible to delegate work whenever there is someone who is capable of doing that because it's beneficial for them to do it. And finally, as a maintainer, it's important to say, I can be as responsive as I can, but not more. So to go into a bit more detail of these points. First of all, as maintainers of community software, you are not making the promise that you will fulfill the wish of every user. That's impossible, and it would definitely hurt yourself. So you need to make clear from the beginning that a community project means you want to help the community, but the community also has to do the work that is acceptable for them. On the topic of combining structure work and architectural work, oftentimes the time that you spend on building the proper architecture for a scientific study is actually useful time because you can reuse that later. As an example, a few years ago, we wanted to investigate and aspect the different ways that different formulations for the Stokes equation, or the different effects of different formulations for the Stokes equation. We could either have created a few different versions of the program that could only run one of the formulations. Instead, we decided to make the individual terms replaceable in the equation. And this fact that now the individual terms are replaceable has led us to several follow-up studies who can now use this to test other modifications. And we have heard from users that that is very useful for them to be easily able to change the equation that is solved. On the other hand, this has a danger, or this might tempt you to over-engineer architecture, which essentially means try to make everything replaceable without a concrete goal or a concrete application. The distinction between these 2 points is not easy to make, but a good rule of thumb is that if you don't have an immediate or worthwhile application of flexible architecture, then don't build the infrastructure for it yet. Only if you can foresee applications that likely need this better architecture, then you can think about implementing it. And finally, it's important that you define the limits that you set for your community work. In many open source developer blogs, for example, burnout is a constant threat to them, both in the sense of just losing interest in the community work, as well as a real mental health problem. So it's important to set limits on the amount of community work that you do. And this leads kind of naturally into the question of how software quality is related to the contributions it gets from the community. So obviously the amount of community involvement is up to each project. So whether you aim for a software that is mostly community developed or a software that is mostly developed in-house or by a small group and just gets a little bit of contributions from the community, that is up to the project. But in either case, you want to provide the resources for members of the community to be able to make these contributions. And the most important of these resources are good documentation and mentoring of people who want to contribute to the project. One important point here and one very valuable process is to review each contribution that goes into the code. But also reviewing contributions needs a certain structure and needs to be done consciously. There was a Better Scientific Software Fellowship in 2018, which discussed how to properly review these pull requests. And one important point, for example, is that you need to keep in mind the abilities of the person who submitted the pull request or who want to make the contribution. You need to explain the problem on their level. Another topic I wanted to talk about is the importance of developer meetings as a tool to increase the size and activity of a community. The plots on the left-hand side that you see are the cumulative number of contributors to Aspect and the committers per month. And the yearly community meetings that Aspect has done for the past 6 years now have clearly contributed to the growth of the total number of contributors and to the number of people who contribute per month. So much so that by now, about 40% of our yearly commits are made at the community meetings. Of course, the number of commits is a very coarse measure because it doesn't reflect the size of the commits or the difficulty of the changes that were made. But these community meetings, and that is consistent across all of the different software projects that I have worked with and that they have talked to, are great opportunities to onboard new members and mentor them into more responsibility and more capabilities. And in order to do that, these new users need to be mentored and they need to be included in the development process. So for example, all participants at one of our developer meetings are expected to contribute to the software during the meeting. On the other hand, the senior participants of the meeting must have the expectation that they spend most of their time advising and mentoring and reviewing. And at least in our expectation, a certain percentage of the participants have to be experienced developers. Otherwise, there is too little time to effectively mentor the other participants. Finally, it should be kept in mind that user meetings are oftentimes not the best time to fundamentally rewrite some core part of the program. It's a better time for expanding it to new applications. Otherwise, there will be too many conflicts and too many too many time of the experienced developers will be spent with this fundamental rewrite. At this point, I wanted to make another quick break and see if there are any questions about these points.
I don't see any questions in the chat right now, Rene.
Okay. One of the common problems that come up in the development of many software projects are conflicts between users working on different features. And this is, in the worst case, that can lead to individual people being very disappointed with the project if their feature is not implemented or not moved forward with into the main software project. So I wanted to give some examples and some possible strategies to work around that. First of all, there is a problem if people work on different techniques that try to solve the same problem. A typical example in mental convection and Geodynamics is the different types of available advection mechanisms to solve the advection diffusion equation. It's hard to say if there is any solution that is universally better than all of the other different techniques. But in this case, if you can develop a modular architecture, this will bring you a long way towards avoiding all of these conflicts because the software can be able to support all of them. Not to say that for a specific application, one of them might be the best, but for other applications, others might be better. And so it's important to combine these approaches. A different conflict could appear if people want to implement the same technique, but want to apply it to different applications. In this case, it can be a problem if people want to write, for example, separate publications, but develop the method in both papers separately. In this case, a good communication culture within the project could allow the people to coordinate the method, to implement the method together cooperatively, and then go on and apply the method for their separate publications. And this creates the question of how to provide proper credit, but I will come back to that. And finally, there are potential conflicts if you have multiple people working on the same technique, but you can often work around that by focusing on different aspects of the technique. So, for example, you could separate the work into a study into the software structure and parallel scalability versus the mathematical accuracy and the convergence orders of the method. In which case, parallel studies can run forward with the same technique. So as a takeaway, in all projects, especially in all community projects that are distributed, these type of feature conflicts are essentially unavoidable. But there are strategies to work around them. And one of the most important one is to be able to discover these conflicts early, for which the project needs an efficient communication culture and a culture where you can trust other people to not abuse the information that you give them. So you need to be, you need to feel secure in telling them what we are working on to make, to discover that they are working on something similar, so that you can use the synergies between the two projects, which requires to have some diplomatic skills and also to be something creative about finding the possible collaborations between the groups. And finally, this makes clear how important it is to share the credit for this work responsibly. And the question of credit already came up a few times during this webinar, and is also discussed widely in other communities. There is a separate ideas webinar, software citation, today and tomorrow, which purely talks about how to cite software. But in this webinar, I also want to talk about some other forms of credit than just citations. Because one of the benefits of community software is, for work on community software, is that it creates a perception of competence or a perception of responsibility for that software. So contributing to a community software creates a sort of social currency within that project. It also acts as a social network. So working within a community software allows you to form more connections to other people who use that software, which can potentially turn into scientific collaborations or future job opportunities or new proposals, things like that. And finally, it also gives the credit of feeling useful. Interestingly, a lot of the developers of open source software projects, not necessarily scientific, but general open source software projects, say that they work on that project just because they like working in that team and they like feeling useful while doing it. So while formal citation is important to give proper credit to people working on software, it's also important to create an atmosphere where people like working with other people and feeling useful working with them. How to apply these general ideas in practice is very specific to the projects. But working with a number of different projects shows that they have similar ways to do this. Possible ways are, for example, to announce contributions to that software in different ways. For example, as an automatic newsletter to all users of the software. And if you're interested in setting something like that up for your software, I have a Python script on my GitHub page that does exactly that. It checks the merged pull requests for a software project and then sends out an email to a mailing list that has the titles and the authors of those pull requests. Other possibilities are release announcements that include all of the authors that have contributed to this release, which is something that, for example, the DL2 project does. You could have release papers that include the main authors. This is a conventional approach. You could have a website that lists all of the active developers. When you give talks, you should make sure to mention that the software is a community software which is developed by many different people, not just the maintainers. And finally, a big way to provide credit to people is to hand over responsibility to them. One of the most common responsibility handover for open source software is to allow write access to the repository, or at least to allow them to merge pull requests. And these questions around credit also play into the question of how to support the growth of members of the community. As I mentioned in the beginning, you don't only want to increase the number of users of your software, you also need users who are more capable of fulfilling more responsibilities and who can solve more complicated tasks. So in general, as a maintainer, you need help. You want more people to help you with the main task of maintaining. And the long-time contributors of your project want credit for their work. So publicly assigning responsibility to them solves both problems in one go. The important part about this is that you need to allow gradual growth. So at each step, people need to prove their competence and their interest in these tasks, and then you can move on to more responsibility. One of the possibilities is, for example, to see who answers questions on mailing lists, who already reviews simple tasks in your software. And finally, it's important for this whole process to establish clear policies about that. Because if you create the impression that all of this is based on the personal feelings of some person or some small circle of persons, then this does not really allow for a transparent growth. It's more like a closed, smaller community which checks who enters the community. So, for example, Aspect has a document called contributing.md on GitHub, which also discusses how principal developers are appointed for Aspect. And it contains criteria. And this is important because, first of all, it shows people that they can become principal developers. A PhD student could see that if I am interested in that project and I do these things, then I could become one of the principal developers. It shows a path perspective. And also it avoids the impression of a closed society that doesn't want anyone to join. And final topic is to manage relations with competitors. Because while I was mostly talking about the community inside a project, the relations with competitors often have an influence on the community itself. And one of the important parts here is to keep this competition professionally. There is a lot of exchange of students, for example, of ideas between different projects. And if this competition becomes too much of a personal competition, then this exchange is usually hindered. It's a very similar story, actually, as trade negotiations between countries. Additionally, it's important to avoid holy wars. Your project will not answer the question whether finite differences or finite elements is the better technique. That's also not the point of your competition with different software projects. Compare facts, not opinions, which can be as easy as saying in this benchmark, this software performs better than this other software, which is not to say that there are other applications where the other software might perform better. Keeping communications open is something that many successful scientific software projects do. For example, there's a lot of exchange between the Patsy and Tridinos communities, which essentially compete for similar applications, but make sure to keep that competition relatively friendly. And it's even possible to just report problems with the communities of competitors or ask for advice for a certain problem that they already solved. One way to keep all of this on a more professional level is to consider the interoperability between different projects. For example, by using relatively standard input and output formats, which make it easier to set up the same problem in different softwares, for example. And finally, having competitors is actually, in many sense, it's actually an advantage for a project because you can see what they do differently. You can see what the communities want. You have a clearer sense of where to go. And you can leverage that as long as you don't create a community which is completely shut off of the other communities because they think this other community is somehow not worthy of their ideas. So these are some of the ideas that I collected from the different software projects I talked to. I would be very happy to receive more ideas. I would be very happy about starting discussions about them. Maybe something of this is just a snapshot from my viewpoint. And I think we could all as a community benefit from discussions about how to lead community software projects. So I would be happy about feedback. As I said, there are lots of resources available already that can help you think about these questions. In particular, the Better Scientific Software website, bssw.io, the HPC Best Practices webinar, and the opensource.guide website by GitHub. And if you take anything away from this webinar, then I would like to emphasize these points, that a software project is equally a collection of source code and a social network, so the people around it, that a successful software project benefits from having a successful community, and that effective community management can prevent or resolve many conflicts in that project and therefore help the project grow. And with that, I thank you for your attention. I'm happy to answer any questions.
Thank you very much, Rene. And at this point, everyone can ask questions either in the chat window, or if you use the raise your hand feature under the participant list, I will unmute your audio. Yes, Juliana.
Yeah, so my question would be over this last year, you've talked to a lot of people who had community softwares, and I was wondering if there's anything you took away from those conversations about what to do better for Aspect, like to manage Aspect's community.
So yes, as part from these conversations, actually the clear definition of policies for how to become a principal developer, that was one of the outcomes of the conversations that I had. Some other important or surprising lessons were how important it is to be responsive to questions from the community. So, for example, I had repeated conversations with users of software projects who said, I started to work with that software and not that other software because I got a reply within a day or two. And the other software project never replied to my question. And this is, by the way, this was also shown in a study by the Mozilla Foundation, which investigated contributions to the Firefox browser, which showed that people who got a reply within a day or two of their contribution were vastly more likely to contribute again to the project than first-time contributors who did not get a reply within the first few days, but had to wait for a week, for example. Okay, so this was one of the outcomes of these talks, that oftentimes people decided to join a community because it was an active community. They got replies and felt welcome there.
Lorraine had a question in the chat window about how many people are currently involved in the OS project in this webinar, thinking about it or want to start one. So what I'm quickly going to do is try and make a Zoom poll to do this.
Okay.
In the meantime, other questions?
I had just a quick comment on your last reply, Rene, is that, yes, I think responsiveness is very, very important to the community, but it's also balanced with having other people also partake in the community by being responsive to questions. So as a very, very senior maintainer, there's sort of that tension between wanting to answer everything as fast as possible, but also giving some time for other people to participate and help others out.
Yes,
right?
yes, absolutely. That's a balance that a maintainer has to strive for, to give enough time for other members of the community to answer questions, to get these members more involved, versus to simply replying to everything as fast as possible.
All right. I will try to open a poll quickly. Let's hope it goes better than yesterday. All right. Can everyone see this poll?
I can see the poll, but I cannot reply. Maybe because I'm one of the hosts. It seems other people can reply, so.
I was successful today because I am not a host.
Rene, I just withdrew your co-host permission, so you may be able to respond to the poll now.
Okay.
Or see it. I will leave the poll up for about a few more seconds, then I'll share it with everyone. And in the meantime, Rene, Philippe had a comment in the chat, and his comment was, in some projects I'm involved in, I notice chat tools like Mattermost or Slack really help newcomers ask questions because the threshold is lower than writing a polished email.
Yeah, that's an interesting observation. So I probably would say I agree. We recently switched from a mailing list for SBAC to a community forum. And there we also see, I would say probably see some more activity from newer users, which would agree with the fact that having some form of asking questions less formally works well, yes. Okay, the poll results suggest that people in this call are generally involved in open source projects, which is not too surprising. Surprising number of people, more than 50%, are thinking about starting an open source project. That's very interesting.
That's a good sign.
Yes. Okay, unless there are any other questions, I thank you all for attending.
Indeed. Thank you, Rene.
Thanks, Rene.
You're welcome.